Hello, and welcome to your second lecture on neural networks and optimization. Last time we ended by talking a little bit about loss functions. Remember, loss functions are metrics that help you assess the performance of your model where lower values of the loss metric are better. Today, we're going to talk a little bit about optimization, which allows us to actually find the values for our model that help us have the lowest loss possible. We're going to start today with something very familiar, which is just a quick review of gradient descent, which we've talked about before. Then we're going to talk about some improvements we can make to gradient descent in order to make it more efficient. So both in the previous class as well as in our data science review, we talked a little bit about gradient descent. Gradient descent is an iterative optimization method which allows you to basically take steps towards a better solution. If you imagine our loss function as a mountain and we want to get to the bottom of that mountain, aka minimize our loss function, we can think of the analogy of a hiker hiking in the pitch black dark. This hiker starts off at some point and they can't see anything around them, but they know they need to get to the bottom of the mountain. Well, one way they could do that is they could get on the ground and feel around themselves and then feel which way is the steepest downhill. Then they could take one step in that direction. And then they could do the same thing, feel around, take a step, take another step, another step, another step. If they keep doing this, they should end up at the bottom of the mountain, aka at a point where our loss function is really low, therefore where our model is performing really well. So the first main idea behind gradient descent is that we want to minimize a loss function. Next, let's talk about how we can actually do that. Really quickly, let's review what partial derivatives are. Partial derivatives help us figure out how changing one variable in a multivariable function will affect the output of that function. For instance, in this multivariable function where it has x squared plus xy plus y squared, we have two variables, x and y, and we might want to ask the question, well, how does changing x affect the output of f? Or how does changing y affect the output of f? In the case of our models, this probably looks like how does changing one of the parameters of our models or the weights of our models, how does that change the outputted loss? Now, I don't expect you to calculate partial derivatives by hand, but I've calculated them for you here, and you can see that this partial derivative of f with respect to x tells us if we hold y constant, how does changing x affect the output of the function f? And this derivative here, the partial derivative of f with respect to y, tells us holding x constant, how does changing y affect the output of f? Now, partial derivatives are great, but we often want to look at all of them at the same time. And one way we can do that is by shoving them all in a vector called the gradient. Here you can see both of our partial derivatives just shoved together in a vector to make the gradient. Because the gradient is just full of partial derivatives, it basically tells us how we should change each of the variables in our model in order to optimize our function f. Here, I made this beautiful plot on the right that represents that x squared plus xy plus y squared function. Here you can see different values of our function, with lower values being in these darker colors towards the middle, and higher values of the function being these lighter colors towards the edges. Remember, our goal is to minimize our functions, and this plot can help us do that. Let's look at this specific point. In this case, it's x is 1, y is 2, and it happens right here. The gradient basically tells us which direction we should step in order to get from this place we are now to a slightly lower value. In this case, this red line represents the gradient, which tells us that direction. This means that if we're starting at this point, we should take a step in this direction in order to help minimize our function. But how big of a step do we take? Well, this on the left-hand side is the update rule for gradient descent. This formula says that whatever values we want to update, we should take the original values minus some learning rate, that's just like a number, times the gradient, which tells us the direction that we want to move. So again, this gradient is telling us the direction that we want to move, and this alpha is telling us how big of a step we want to take in that direction. So for instance, I could take a step that's this big, or I could take a step that's this big. all of that's determined by our learning rate alpha. And while in 2 dimensions, like in this picture, it's really easy to just think of a gradient as a direction that we take a step in. Once we get to have a lot of different parameters and have these really long gradients, it can be more useful to think of the gradient as having individual adjustments that we should make to each of our parameters. Each of those partial derivatives tells us what changes we should make to that variable in order to help minimize our function. Just so you can see what this looks like, I've plotted here our contour map with the addition of something called a gradient field. A gradient field just basically takes all of the gradients for all of the points on this map and shows them using those arrows. So basically, this tells you that if I started right here on my plot, I would want to move in this direction, the direction that arrow is pointing. However, if I started, say, here, I would want to move in this direction, the direction that the arrow is pointing. So basically, you can see, depending on where you start in this plot, we can use the gradient in order to minimize our function, no matter where we start. All right, so that gave us our second idea. The gradient tells us what direction to move in order to minimize our function. In other words, the gradient tells us for each of those terms in the gradient what adjustments we should make to the different parameters or variables in our model. Now, I mentioned before with that update rule that the learning rate controls how big of a step we take. And just generally, we don't want our learning rate to be too big or too small. If our learning rate is too big, we tend to bounce around minima and maybe never even converge. With a small learning rate, we're taking teeny tiny little steps. So while we may converge, it'll take a very long time. So we sort of want to be in that Goldilocks zone of having a learning rate that's not too big and not too small. Interestingly, we actually often do not want a learning rate that's constant. It can be really beneficial to start off by taking bigger steps and having a bigger learning rate, and then slowly bring that learning rate down as we approach a minima that's going to optimize our function. So far, we've been talking about using a constant learning rate. That parameter alpha is the same throughout the entire gradient descent process. However, sometimes we might want to use learning rate decay, which basically starts with a larger learning rate and then slowly tapers it off throughout that process. The formula that you can see on the screen just gives you one example of how we could taper a learning rate by just making it a little bit less every time we process a batch of data. All right, and that's the last big idea of gradient descent. The learning rate controls how big of a step we take. Too big and we're going to bounce around, too small and will take forever to reach anything. And also we talked about the idea that we may want different learning rates at different parts in the process. All right, and that's the big ideas of gradient descent. Last, we talked about the learning rate controls how big the adjustments or steps that we take are. Too big of a learning rate and we're going to bounce around all over the place. Too small of a learning rate and will take forever to get anywhere. We also talked about the fact that we may want different learning rates for different points in the process. Maybe we want to start with a big learning rate and then slowly taper it off. All right, so let's go over a quick example with linear regression. And this is going to be the simplest linear regression because it only has one predictor. That means there are 2 parameters in our model, the intercept and the coefficient for that predictor. For simplicity of math, we are going to use the sum of squared errors as our loss function. This measures the squared error, so the squared distance between our model's guess and the actual value, as a way to measure model performance. Of course, we know that linear regression makes predictions using this formula. The predicted value is going to be the intercept plus the coefficient times our predictor. When I plug those 2 together, you can see the math here. This ends up being the final version of our loss function that incorporates the way that linear regression makes predictions. Using that formula that we ended on, we can take the partial derivative of it with respect to both our intercept and our coefficient. Remember that our 2 variables that we have control over in our model are that intercept and coefficient. So we might want to know, how does it affect our loss when we adjust either the intercept or the coefficient? Now, again, I don't expect you to be able to calculate this by hand, but you can trust me that this is the gradient for both of our variables, the intercept at the top and the coefficient at the bottom. Now, of course, with gradient descent, we always have to start somewhere. So just to make our math easier, I'm going to start at the point 0, 0, and we're going to see how we can change those two parameters from 0, 0 to something that maybe minimizes our loss function a little more. Here you can see that gradient that we calculated on the previous screen, and here you can see that same gradient, but I've plugged in 0 for both the intercept as well as the coefficient. If you take a second to look at what the gradient is, it should sort of make intuitive sense, because if you think about a linear regression with intercept and coefficient being 0, that just means we're going to predict 0 for every single data point. So I've moved this gradient over here, but of course we need to plug in some data points to see what the actual loss values are to calculate our gradient. Here, because we're lazy, we're only going to have 2 data points. These are the data points 1, 1 and 2, 3. That means x is 1 and y is 1, x is 2 and y is 3. So every time I see an x or a y in this formula, I'm going to go ahead and plug in these numbers. For example, this 1 comes from here, this 3 comes from here, same thing here and here, and then of course our x's come from here and here, here and here. So you can see that all we've done is we've plugged in our 2 data points into this gradient function. Once we've done all of that math, we get out this gradient, -8, -14. This tells us what adjustments we should make to the intercept on that top value and the coefficient on that second value. Notice that the partial derivative for the coefficient is actually larger in magnitude than the one for the intercept. That means in this specific case, we actually want to change our coefficient more than we want to change our intercept. All right, so let's apply our update rule for gradient descent. Remember, in gradient descent, the new values for our parameter are the old values, which we set to be 0, 0, minus our learning rate, which I've set to 0.01, times our gradient. Once we do all that math, we get these new parameters of 0.08 and 0.14. Just to do a quick sanity check, let's make sure that our loss function actually was reduced by taking that step. This top formula shows us what the loss was when we had our original variables of 0, 0 for both the intercept and the coefficient. Plugging in our 2 data points, you can see that our loss, the sum of squared errors, was 10. When we plug in our new parameter values, again, that's our coefficient and our intercept, and we plug in our 2 data points, we see that our loss does actually go down. Now it's around 4, where it was before around 10. So we did in fact help reduce our loss function by changing our parameters according to the gradient. If you're someone whose brain works a little better in code than with math symbols, here's the code from our data science review classwork where we originally covered gradient descent. This basically does exactly what we did together using math, but with code. Here we're creating a data frame with our 2 points, 1, 1 and 2, 3. And here this function gradient actually defines how we would make an update using gradient descent. Here we calculate the gradient using all of our data points, and here we apply our update rule by taking our old values for the parameters and subtracting the learning rate times the gradient. Now that we've talked about the basics of gradient descent, let's talk about a couple of tweaks that we can make. Now, with regular vanilla gradient descent, often called batch gradient descent, every time we estimate the gradient to take a step, we use every single one of our data points in order to do that. Now, of course, that's computationally expensive, but it does make sure that we are efficiently moving downhill. However, sometimes we may not want to use all of the data points to estimate the gradient. In fact, we could even just use one. When we use a single data point to estimate our gradient at every update, we usually call this stochastic gradient descent. Now, this is a huge improvement in computational efficiency because instead of processing thousands of data points every time we estimate the gradient, we only need one. However, it does lead to a little bit of zigzaggy steps that are all over the place. Sometimes people refer to this as a drunk man walking downhill because that's kind of what your updates will look like. So we get a lot more computational efficiency, but the estimates of our gradients are kind of all over the place. So often we want a bit of a middle ground. In comes mini batch gradient descent. With mini batch gradient descent, we don't use all the data points to estimate a gradient, but we do use a handful, maybe 32 or 64, and that way we still have the computational efficiency of similar to a stochastic gradient descent, but we don't have as much of that drunk man walking downhill stuff going on. All right. Quickly before we move on, I just want to update the notation I'm using. In the previous examples, we used this update rule, which said that the new values of our parameters are the old values minus some learning rate times the gradient. Now, we're still going to do that, but I just want to update the math notation because as we have more and more parameters, it's really not efficient to write out the entire gradient like this. Instead, I'm going to write it like this. Same idea. New weights are equal to the old weights minus a learning rate times the gradient. This is just a little bit easier to write. All right, so we finished with gradient descent. We learned a bunch of different things, including that the gradient uses partial derivatives to tell us how sensitive our loss function is to changes in our different parameters. In other words, it tells us how to change our different parameters in order to minimize our loss function. In order to update our parameters, we use this update rule where our new weights are equal to our old weights minus a learning rate times the gradient. Learning rates determine how big of a step or how big of an adjustment we make to our parameters. Large learning rates can lead us to bouncing around everywhere, whereas low learning rates can cause us to take a really long time to get anywhere. We also talked about some improvements we can make to gradient descent, like using stochastic gradient descent or mini-batch gradient descent, which don't use all of the data points to calculate the gradient and therefore improve our computational efficiency. Now, gradient descent is great, but it does have a couple of problems. One of those problems is that choosing a learning rate is really difficult. And not only is it difficult, even if we use one of those learning rate decay functions that starts our learning rate off high and then slowly makes it lower, that is really difficult to choose ahead of time. Next, it can also be difficult to use the same learning rate for every parameter in our model. Maybe for some parameters we want to take big steps, but for other parameters we want to take small steps. Gradient descent uses the same learning rate for all of our parameters. Lastly, depending on the step size, gradient descent can actually get stuck in local minima and miss a global minimum, or it might get stuck on something like a saddle point. So let's talk a little bit about some improvements we can make to gradient descent in order to address or maybe even overcome some of these problems. We're going to talk about a bunch of different optimizers that improve on gradient descent, and this is sort of the map of how we're going to talk about them. First, let's start off with momentum. Just like momentum in physics, momentum in gradient descent basically allows us to build up speed as we're descending a gradient. Our previous update rule said that our new weights are equal to our old weights minus the learning rate times the gradient. Well, the momentum update rule looks very similar, except instead of using the gradient to update, we use this momentum variable. But you can see that the momentum variable is basically just a moving average of all of the past gradients. Momentum has this really nice property of smoothing out the steps that we take. Let's imagine that without momentum, our gradient descent asks us to sort of make this type of step as we approach the minimum. Well, that does a lot of zigzagging back and forth. With momentum, because we consider the moving average of the gradients that have come before, that means the gradients at previous steps impact how we'll move on this step. So instead of that back and forth motion, we actually get some smoother steps because we're taking the average of the gradients every time we take a step. This also allows us to build up speed if gradients are consistently in the same direction. This means that if we have something like a local minima and we're going down, we're building up speed as we go downhill, and that speed can persist and actually kind of shoot us out of a local minimum, allowing us to hopefully approach this global minimum. So momentum, with a very simple change to our update rule, allows us to build up speed as we go downhill in our gradient. If all of the previous steps of our gradient were in the same direction, we're more confident that we're going in the right direction. However, if all the previous steps were in different directions, we're less confident, and momentum sort of smooths out some of that back and forth. Because of this buildup in speed, momentum can, in some cases, help us converge faster than gradient descent. And it has the added benefit of, in certain situations, allowing us to escape some local minima because we've built up speed as we've been descending the gradient. All right, momentum down. Now let's talk about the eta grad optimizer. While momentum affected the gradient part of our update rule, eta grad affects the learning rate part. We talked about earlier that we may want to change our learning rate throughout the process of descending our gradient. But in regular vanilla gradient descent, we use the same learning rate across time. We also use the same learning rate for each parameter. Eta grad introduces two really useful updates. First, we actually have a different learning rate for each feature. That means that different parameters in our model can have big steps and other ones can have smaller steps. Next, our learning rate is adapted, that's where the eta in eta grad comes from, based on the sum of the squared gradients that came before. Here you can see the change to our update rule does in fact affect the learning rate. What we do is we take our baseline learning rate alpha and we divide it by the square root of the sum of the squared gradients from all the previous steps. This little parameter here is just a very tiny number like 0.0001 that prevents us from dividing by 0 at the beginning of our process. Because we're taking the sum of our squared gradients, this number in the denominator can only ever increase. That means that at the beginning of the process, it's going to be pretty small. But as we go through the process of taking more and more steps, this sum of past gradients is going to be bigger and bigger, which will cause our learning rate to get smaller and smaller because we're taking a fraction where the denominator is increasing. This basically automatically does that learning rate decay for us that we talked about before. So instead of having to set hyperparameters and choose learning rates ahead of time, eta grad allows us to adapt during the process. So these are huge improvements. We no longer have to hand tune a learning rate, and we no longer have the same learning rate for every single parameter. But we still have a little bit of an issue with eta grad. If you notice in the formula, we said that this sum of the past squared gradients can only ever increase because we're taking the sum of, by default, positive values. This means that our learning rate decays, and it can actually decay really quickly. And once our learning rate is really small, that means we can't actually learn anything about our parameters because the step sizes we're taking are super tiny and not actually changing our parameter value. Well, root mean squared propagation, aka RMSP, to the rescue. RMSP improves on eta grad by changing that term in the denominator. Whereas before we had the sum of the squared gradients in the denominator, here with RMSP, we have this new term. And this term is the moving average of the previous squared gradients. So instead of taking the sum where we just kind of build more and more gradients in, creating an increasing value, we instead take a moving average of the previous squared gradients. This means that as time goes on, previous or earlier gradients have less and less influence on what this value is. This allows us to take advantage of having a different learning rate per each parameter and adapting the learning rate throughout the process without having the risk of having our learning rate slow to absolutely nothing towards the end of our process. This parameter beta basically controls that weighted average. We typically set beta to be about 0.9. So eta grad's learning rate got smaller and smaller as time went on because that sum of squared gradients can only ever get bigger. However, RMSP solves that issue by instead replacing that denominator term with a moving average of previous squared gradients, meaning that as time goes on, earlier gradients become less and less important. All right, so we talked about how momentum changes the gradient term in our update rule. Instead of just considering the current gradient, we consider a moving average of past gradients. That means that the gradient at previous steps might affect the direction we move at this step. We also talked about how eta grad and RMSP affect the learning rate of our update rule. We talked about before that we might want to change our learning rate throughout the process, and we may want to use a different learning rate for each parameter. Both AdaGrad and RMSP allow us to do so, with RMSP making the additional improvement of making sure that our learning rate doesn't just go to nothing as the process goes on. Now, you might think, well, both of those things sound really good, both momentum and adaptable learning rates, and you are correct. And that's where we put these all together to get the optimizer ADAM. ADAM truly takes the best of momentum and RMSP and shoves them together. The update rule for ADAM looks like this, and let's take a look at it piece by piece. First of all, it looks really familiar. New weights are old weights minus some adjustment. But you might notice some very familiar terms, like a momentum term and this denominator term for adapting our learning rates. That's because these terms are from momentum and RMSP respectively. In ADAM, instead of the gradient, we use the momentum term in order to choose the direction of our steps. Again, momentum just takes a moving average of previous gradients, which allows us to build up speed and smooth out any zigzagging steps we might be taking. And we also have adaptable learning rates. Here you can see we have the same learning rate rule as in RMSP, where we take our original learning rate and we divide it by the moving average of the previous squared gradients. Of course, using this moving average, we improve upon the AdaGrad method, where our learning rate might slowly go all the way to 0, causing us to not be able to learn anymore. One additional advantage that ADAM has is it actually unbiases our momentum and that adaptive learning rate term. When we start out our process, we often initialize our previous gradients to be 0. And so as we start building up gradients, our two terms, which rely on our previous gradients, are biased towards being 0. In order to overcome this bias, which really is only in effect in the first couple of steps that we take, ADAM actually uses a formula listed here and here to unbias these estimates. The t's in this formula represent the time step, or the number of iterations. You can see that the 1 minus beta to the power of t is going to get closer and closer and closer to 1 the higher t is. So that means as time goes on, our adjustment gets less and less, meaning it really only affects those first few iterations. So ADAM takes the best of momentum, where we can build up speed and smooth out zigzagging steps, and of RMSP, which allows us to have adaptive learning rates for each parameter based on the exponentially decaying sum of the squared gradients. ADAM also has the advantage of unbiasing the momentum and learning rate terms, so that as we take our first few steps, those terms aren't biased towards 0. ADAM typically tends to be sold as the state-of-the-art optimizer, although there are improvements that have already been made to it. Now, I won't say that ADAM is always the right tool for the job. It's pretty much agreed upon that we often want some type of optimizer that allows us to have an adaptable learning rate. But there's certainly certain situations where stochastic gradient descent works better, or ADAM works better, or AdaGrad or RMSP work better. So often, if you're having issues, you may want to try different optimizers. To review, today we just talked about a lot of optimizers. We started out with our vanilla gradient descent and then talked about a couple of improvements like stochastic gradient descent and mini batch gradient descent that allowed us to make a little bit of an improvement in the computational efficiency of gradient descent. Then we talked about improvements we could make to our gradient descent update rule. First, we talked about momentum, which allows us to change the gradient part of the update rule. Instead of just using our current gradient, we use a moving average of previous gradients, which allows us to smooth out the steps we're taking and to build up speed. Then we talked about the fact that using AdaGrad and RMSP allow us to have adaptable learning rates. Instead of having to set a learning rate schedule or just a plain basic learning rate ahead of time, both AdaGrad and RMSP individually adapt our learning rate for each parameter, as well as adapting the learning rate through time. When we combine these two insights, we get the ADAM optimizer, which takes advantage of both momentum as well as adaptive learning rates. All right, that's all I have for you. I will see you next time.